Sorry, wrong show, everyone. This is the right show. Welcome back, friends. Today we have a special guest with us today. You might know him from his famous work, Angels and Demons and Relativity. Please welcome Mortiz Cornelius Escher from the dead.
Please call me Dr. Escher.
You're not really a doctor, though.
I just like the way it sounds.
Okay.
Oh, hold up. I need to take off my clown goggles.
Okay, so we want to know, like, you outside of your work.
So, you want to know about when I was born?
Not really. These days we can just Google that. We really want to know, like, the men behind the work, like your childhood, your early life.
Well, I lived in the Netherlands, but I was never really into Common Core school. Always had my head in the art room. Later life, I traveled a lot to Italy, Spain, Rome, did a lot of backpacking.
Okay, so let's talk about your art, like what kind of art you did.
Well, before 1937, I really focused on landscaping art and agricultural art. And then after 1937, I focused towards the division of planes.
So like more like mathematical art.
No.
Oh. Yeah, I did hear a rumor that you really didn't believe in art. Is that true? I mean, in math.
Hocus pocus. All of it. Hocus pocus.
That was very interesting. Now let's welcome a new guest who knows more about the hyperbolic plane and relates to Escher.
Well, thanks for having me. It's good to be back and see my old friend Escher again.
Okay, so let's talk about how you guys got acquainted.
Well, so I first encountered Escher and his art at the 1954 International Congress of Mathematicians, which was like a big conference thing. And I saw some of his art and I wrote to him and I was like, hey, the math and the symmetries of this art is really cool. And then about 3 years later, I was writing an article about symmetries and tessellations of the Euclidean plane, the Poincare disk model, the hyperbolic plane, and on the surface of a sphere. And I wrote to Escher to see if I could use some of his symmetry drawings to illustrate my article. And he was like, yeah, of course. So after I wrote my article and illustrated it, I sent him a copy. And one of the figures caught his eye. It was figure number 7, but that doesn't mean anything to you guys because you can't see it. But anyways, it caught his eye because it modeled infinity in a finite space. And so he wrote me back and he was like, hey, how can I do those tessellations? How can I tessellate this hyperbolic plane or tessellate this infinity in a finite space? And I wrote him back and I was like, hey, you can tessellate it by drawing orthogonal circles to infinitely till you get to the boundary of the circle because this model's infinity. That was it.
I'm gonna be honest with you, I really didn't understand not one word Oscar just said.
Yes, neither do I. Such hocus pocus is exactly what he wrote back. When I inquired about how I could put more circles that approach the edge of the disk, I asked for simple explanations, and he responds with nonsense about hyperbolic geographies and 3s and 7s.
Geometries.
Needless to say, I understand nothing of it. Instead, I continued my construction using a compass and straight edge to draw circles, and eventually figured it out for myself. I found out I could construct lines by drawing circles that intersect the boundary circle at a right angle, and continued doing so infinitely. This gave me a way to model infinity in a finite space, which I had been trying to do for many years. I was always bothered by how my tessellations would be cut off mid-figure.
That's literally what I just said, but go off, I guess.
Dude, that was even English.
Okay, well, to clarify, hyperbolic geometry, which is what he was tessellating, the Poincare disk, hyperbolic geometry is kind of like Euclidean geometry, which is like regular, like 2D geometry, you know what I'm talking about? Like you would have learned in school. Except that the fifth postulate, which is about parallel lines, is different. So in Euclidean geometry, you can only have one parallel line, excuse me, going through point P that's parallel to a line L. But in hyperbolic, you can have infinitely many lines. So that's why you can model infinity in a space that's small. And as far as how you construct lines, this is how you construct lines.
That's how I constructed lines.
Okay, so what you do is you have this circle in the middle, and you pick any point, like out here, and you draw a circle around it, and then it's a line. And that's what I told him to do.
That is what I did.
He's just not the brightest.
Better than you.
Are you?
I did that.
You don't even believe in math.
Hocus pocus. Hocus pocus.
All right, thank you, HFM Coxter. All right, moving on. Also, from your tessellations you have made, you've also made very trippy illusions. So we have a special guest, another special guest with us here, Sir Roger Penrose.
Hello, everyone. Thanks for having me.
It's our pleasure.
Hold up. I don't think they can see her over this.
Oh, that is very true. Okay, so how long have you and Escher known each other?
I first met Escher at the International Congress of Mathematicians in 1954, where he was giving a lecture on his art, and I was very fascinated by the impossible geometry and illusions that he had in his work, so I was inspired to create an impossible figure of my own, and that's how I ended up creating this impossible triangle, more commonly referred to as the Penrose Trabar.
And what's so special about it?
Well, it's a triangle that can be drawn in perspective on paper, but can't actually exist as a solid object in three-dimensional space.
Interesting.
Mm-hmm.
But why is that? It looks pretty realistic to me.
Well, we can do what we mathematicians call a proof by contradiction to show that it's impossible. Let's first suppose that the Penrose Trabar is a real object. We can define it as a set of line segments that form three figures lying in different intersecting planes, such that each part of the trabar that is a different color lies on a different plane. Let's start by labeling a couple of the segments A, B, and C. We see that segments A and B intersect at a point alpha. A is part of plane 1, and B is part of plane 2, meaning that alpha is part of both planes 1 and 2, an intersection point. The only other place where planes 1 and 2 intersect is along this line segment C. This is a violation of the axioms of Euclidean geometry because this intersection point is all alone. It's not part of a line. And according to the axiom, planes can't intersect at an isolated point. Therefore, we've arrived at a contradiction in assuming that 1, 2, and 3 are distinct planes, and therefore, the Penrose Trabar cannot exist in 3 dimensions.
Uh-huh.
My sentiments exactly. It's all a bunch of hocus pocus. But anyway, in 1958, Penrose wrote an article about the Trabar in the British Journal of Psychology and sent a copy of it to me. I became interested in the object and the illusion itself and wanted to incorporate it into my work, which is what I did in my 1961 lithograph, Waterfall. I used 2 Penrose Trabars to represent a waterfall that appears to supply its own water, which seemingly flows from the bottom of a waterfall downhill along a winding path until it unexpectedly reaches the top of the waterfall again. This illusion is called a visual paradox.
What's your problem, old chap, pretending that your art has nothing to do with maths? Perhaps if you wouldn't scorn it so much, you would have actually been able to complete print gallery. Ooh, what's that?
Ooh, what is that?
He's talking about my 1956 lithograph, Print Gallery. It's another type of illusion which depicts a man standing in an art gallery looking at a picture of a seaside town with a row of buildings, one of which, he realizes, is the very gallery he is standing in. My idea was to create a continuous cycle expansion without beginning or end, in which the man looks into the painting and sees a copy of himself looking at the painting, which contained another copy of himself looking at the painting, and so on forever. Alas, I couldn't crack the puzzle and ended up leaving a blank hole in the center of the piece.
Chump. Another mathematician named Hendrik Lenstra succeeded in solving the problem. In making the piece, dear old Escher had drawn a model of the picture in a normal square grid and then transferred it onto a special grid that he made himself. As you can see, it's quite curvy and distorted, and the size of the squares in the grid decreases as they approach the center. Lenstra thought of this picture as being drawn on an elliptical curve over the field of complex numbers, and combining this information with an analysis of the distortion of Escher's grid, he was able to calculate that the center of the painting should contain a copy of itself rotated clockwise by just shy of 160 degrees and shrunk down by a factor of 22.5. Using a computer, he was able to finish the lithograph as Escher had envisioned over 50 years later. As we can see, there is no blank patch in this copy, and if we zoom in farther, we can see that it's filled by a copy of the picture, rotated and shrunken down. And if we zoom in again, we see that this copy has in itself another copy, and so on forever, in what Lenstra deemed the Drost effect.
But Escher still gets a lot of credit for that, since he's the first one to actually make the illusion.
This is true. He did come up with a very sophisticated, and though he may not admit it, mathematical idea based on the concepts of infinity and repetition. And he also devised that whole grid despite having very little formal education in maths. Brilliant bloke.
We'll be right back. We're back. Unfortunately, from our producers, we were kicked out from HPU Library, so now we're in the bottom, but we're still recording. Anyways, so now we have a new guest. It is a random modern mathematician, Hannah. Hello, nice having you today.
Hi, thank you. I'm just here to tell you some really great facts about Escher, and he actually left a really big impact on the world.
Okay, so how is he related to modern mathematics today?
Well, it's funny you ask because the answer is really ironic. Despite his denial of mathematics, a lot of his, most of his art was actually heavily influenced by math, and he was very much aware of how crucial of a role math played in his art. So would you like to hear some examples?
Yes, actually.
Okay, so one of his most famous prints, Reptiles, was used in a chemistry textbook for crystallography of all things. And so that was really cool. Another piece, Sky and Water 1, was used by a Norwegian geologist named Rosenquist, as well as for fields such as physics, chemistry, and even psychology. The stark contrast and transitions between the birds and fish and the light and dark and between sky and water, as the title implies, is just great for analogies. And another piece of his called Horseman was used by Chen-Ning Yang for his elementary particle physics experiments. It was a really great representation because of the asymmetries between the upper and the lower horsemen.
So not only was his art used in math, but also scientific.
Yes, it was really amazing how art can be used for such scientific purposes.
All right, Hannah, everyone. Okay, everyone, that was our last and final guest, Escher.
Dr. Escher.
Oh, I'm sorry, Dr. Escher. Do you have anything else to say before you go back to your grave?
Just that I wish for world peace.
Escher, last time I saw you, you wouldn't let me use your art as my album cover.
Mick Jagger. You call me by my first name. I don't like that. Hand me my hand warmers.
Let's dance, buddy.
Security!
We'd just like everyone to know that no mathematicians were harmed in the making of this video.
Bye.